Okay, so we start the eighth presentation of our talk cycle. So we have Giuseppe with us, and thank you so much for accepting our invitation. I think you can go ahead, share your screen, and talk about the ethics for NLP. We're very excited to hear about that.
Okay, let me see. You should be seeing. I don't know if you're still seeing the. Do you see the full presentation or the keynote page?
That's the presentation.
Yes, we're seeing the cover of your presentation, I think.
Okay, cool. Okay, so full screen mode. Okay, cool. So, okay, let me start. Thank you for having me. Thank you for the invite. It's always nice to, collect feedbacks and discuss about topics, basically my research topics with someone new. So thank you for the invitation, and I hope you'll enjoy the talk, which is about interpretability, the idea of understanding in a way what's going on when we use language models to inform a fairer NLP in general. So at the end of the day, we want to have a non-discriminatory set of tools. And the main line of research here is we want a way to understand what's going on to then tune the models to produce a fairer output. So let's say, I should give a very, very short introduction. I'm a postdoctoral researcher at Mila NLP, in the Mila NLP group in Bocconi University, Milano, Italy. And as I said, my main research areas are transparency, fairness of language technologies. And what I mean by transparency and fairness, at the intersection of the two, I mainly research on how to make interpretability choices. So choices based on interpretability insights that we can find in the models to mitigate many types of unfair behaviors that we see out there. And I'm recently also interested in working on safety related research in a way that, again, we should be able to deploy models that are not going to produce real harms in real world and society. So in the next, say, 45 minutes, I will talk about interpretability for fairer NLP technologies, and specifically first motivating it. So why do we even need that? Then to get everybody on the same page, I'll go over some overview of what's interpretability today on NLP. And then review with you some recent research on interpretability for fairness, and specifically group fairness. So we want a model that is fair across different groups in the training data. And then I will introduce very briefly some challenges and ideas that are currently being studied in the field, and specifically I will bring to the table the two papers that we recently published, Ferret and A Tale of Pronouns. So let me begin with the motivational part. Why do we even need the interpretability part? Nobody likes black boxes, right? So we do have a way to interpret what's going on. We do have a set of tools that can help us in getting to that result. So we could use that, and we could use that to ask questions such as, is the model, when we have a good result, when we have a good prediction, for example, if we are in a classification task, we can ask, okay, is this right for the right reason? Or let's if it's wrong, let's do some debugging steps and, you know, approach it in a debugging perspective. And this is increasingly, important in today's activities and world, because many more people are approaching language technologies, using language technologies. Their everyday life activities are shaped around language technologies. So that's why we should be able to provide that kind of insight. Once we have a good way to measure what's going on in this kind of language models, or also other kind of language technologies, we can detect probably, but also mitigate social biases through the use of interpretability as a control signal. And of course, nobody likes black boxes, but now it's also a matter of official requirements. So interpretability is required by the EU and other global entities. This is an excerpt from the recent ethics guidelines for trustworthy AI. This is EU-based, but in all over the world, we're seeing that more and more requirements are requested to whoever is deploying a language technology, or a more generally speaking, a machine learning based technology. So yeah, that's whenever an AI system has a significant impact on people's life, it should be possible to demand a suitable explanation on AI systems decision-making process. This is pretty clear to me that policymakers are asking us to do that. So of course, if you have questions at any time in the talk, we can have it interactive. So feel free to interrupt me, or we can just take everything at the end. So yeah, to get everybody on the same page, like a super quick overview of what it is interpretability in natural language processing today. Because the field has changed a lot during the recent years. Like in NLP itself has changed a lot. So yeah, I want to give you some intuition on that. So this is something that comes also from other machine learning fields, especially vision, machine learning for computer vision. And what I'm talking about is gradient-based methods. So you have some measurement that you can measure across different points in the space. And what you could do, you could, in a way, ask by looking at the gradients, which direction you should be following. So in which direction you should go to increase the probability of a specific class label. So what you see in the top right part of the slide. So if I can measure that, and if I can have the gradients, if I can observe the gradients, I can just follow the gradient to any specific direction, and I can increase, for example, the probability of a class, or decrease the probability of a class label. So as you can see in the top right image, if darker colors mean higher probability, if you go up and down, so if you increase or decrease x2, the probability is not changing much because you're in a sort of valley, let's say. But if you increase x1, which is the bottom axis, you see that the probability of a specific Y class is increasing. So yeah, that's a general overview of the idea behind gradient-based methods. Of course, when you deal with NLP, your input features are not just x1 and x2. You have a token, and actually a set of tokens. And for each token is n-dimensional. So you have, if you have worked with transformers or recurrent neural networks, you know that the input tokens are multi-dimensional things. And so you will need some sort of aggregation. Now, in the neighborhood of a single point, there might be some local irregularities of the loss function. So what people have been thinking about is, let's use some smoothing approaches, some integrated based approaches. And here I've reported two of the most famous ones, multigrad and integrated gradients, which they give you a more reliable estimation of the gradient. And then once you have the gradient, you can go in the space wherever you want to go. But there's another option, which is quite used in the field, the idea of using surrogate models. So let's say you have a classification task and you have a sentence, you are a smart dude. What you can do is sampling the neighborhood of the instance, and you can do this sampling basically by masking some of the words. If you just mask dude, for example, you have another sentence which we can assume, and there are restrictions about that, but you can assume that the new sentence is within the neighborhood of the first one, or the original one that I want to explain, and you can keep sampling from the neighborhood, and you have a set, a new, let's say, local data set that you can use to collect the model predictions. So you compute the prediction for every sample in the data sets. So you have a new prediction of for each of the samples in the data set, in this local data set. And then since you have the X and you have the Y for your model, you can train in the locality of the neighborhood a simpler, we call it surrogate model, which is typically like an inherently interpretable model, like a logistic regression or a decision tree, for example, if you have a low number of features. And so in that locality, the big model that you want to explain is approximated by the surrogate model. And some of the most famous approaches on surrogate models are line and sharp. A final slide on what kind of interpretability we can do today on NLP is counterfactual and contrastive approaches. So counterfactual approaches ask the following counterfactual: what's the minimal edit to change the model outcome? So as you can see on the right, you can ask, so let's say you have a question answering task, Anna and her children are going to Linda's home, and you have to predict which one is the right answer. The prediction can be originally is by train, given the context, but what you can do is also asking, for example, why is it by train? What's the minimal amount of tokens I need to change the prediction, for example, from by train to on foot? So if the contrast prediction is on foot, you can see what changes in the original context. And that is basically your explanation, because that's what's changing. So that's what the model used to predict the original, to give the original prediction. And mice and polyjuice are some sort of two of the most famous approaches for counterfactual explanation. Then you can also use contrastive, which is kind of related but different. You can compute the importance of each token in the sentence for a specific prediction. So let's say you have a sentence completion task. So can you stop the dog from, and the model is predicting barking. So you might ask the model, for example, you can compute the integrated gradients, since we have talked about that. So you take the gradients and you say, okay, to predict barking, I think, given the gradients, the model has used can and from, for example. And that's kind of, probably not the best explanation that you can have. But if you find a way to ask, okay, why did the model predict barking instead of crying? So here is the contrastive part. Or instead of walking, you can see that the gradients are changing. So of course you have to implement this in a specific way, but you can see the gradients are changing towards other tokens. And this is a work recently released on contrastive explanations. So there are other approaches, of course. That's my intention, is not to be super comprehensive on every little, detail and method within each family. But we can always discuss about other approaches. Those are some of the most used ones. So with that, I would be okay with the primer on interpretability on NLP, and I would rather move to the most interesting part of the talk, which is how we're using these numbers to climb towards a fairer set of models. So when I'll be talking about fairness in this presentation, I'll be almost always referring to group fairness. So the idea that the model should be as good as for every group, as good as any other group. So you don't want to have disparities, for example, in performance across different groups, which are, for example, identifiable in your training data or in your testing data or in your set of customers if you are deploying a model. So yeah, that's basically group fairness. And it's so when a model has, you train your models, and you train your models from data that comes from the internet, and then you train your models by making some decisions if you are the designer of the model. So every step of the pipeline, the people who are designing the model, people who are selecting and picking up the training data, many like the actual training data that you sample can bring some bias in the pipeline, some biases in the pipeline. So the research has been characterizing these biases into representational biases, locational biases, intrinsic and biases. Basically, what we are trying to map in this specific moment of time is what's inside. So what are the encoded social biases in language models? And what's happening typically is that you have a dominant group and a minority group. And when you look at what's happening, what's the representation, for example, of those two groups, you can see that they have a biased representation. I'll get to some examples in a while. Or when you see some mention of those groups in your text, the performance of the model changes drastically, regardless of the context, just because some of the groups has been mentioned in the text. So yeah, and in terms of performance, when I'm talking about performance, you can measure group fairness by, you would like to have a positive, for example, a similar accuracy, similar F1 score across the groups, but most importantly, you also want to have the similar error rates, so similar precision, similar false positives, a similar number of false positives and false negatives. There are a bunch of metrics that can help you in measuring that. So yeah, there's some work that, not like an extended set of works on that, but something has been done recently on interpretability. Here is called XAI, explainable AI in short, for mitigating biases in language technologies. So yeah, there's this paper from Kennedy and colleagues from 2020 that basically addresses the task of hate speech detection. Whenever you train a model on a hate speech detection dataset, what can happen is that for some selection biases, in the way you sampled your data, you can find that most of the times that a specific group represented through some identity terms is associated with a specific class label. So the model becomes over-reliant to the presence of the identity term. And that's what the authors call unintended bias, because you want to take your decision. Your hate speech detection model typically address a binary task. So you have to decide whether a text is hateful or not. And you want to take the decision you want to make the decision regardless of any triggering identity terms. So, for example, see, there is an example on the right, debemos impedir la discriminación de los homosexuales. This is clearly not hateful, but you don't want the model to take the decision just because homosexuality is in there. That's the identity term I was referring about. So what they do is compute interpretability scores. They use a specific method. They compute interpretability scores and the importance that they achieve. So they compute, they measure in terms of interpretability importance. It's something that they insert in the loss. So if it's a classification task, that's going to be a binary classification loss. You can have a regularization term to that loss because you want to force the model to observe in a way less the identity terms that are in the training data. So let's say you're trying to regularize, I don't know, the minority of homosexuals, individuals. So you just collect a set of identity terms where you specify, if it's Spanish, for example, homosexuales, gay, and whatever. So that requires a list of identity terms. But it's something that it's pretty easy to compute, and it's differentiable, so you can include that in the loss of the task. So more recently, 2022, Matthew and colleagues have collected human rationales, so basically binary maps that tells you what are the tokens that are more relevant, important for a prediction on a set of hate speech data. And they basically matched those human rationales with the model attention. So since it's a transform, most of the times is a transformer language models, you want to match the attention with the human rationales so that the model is observing what the authors have observed, what the authors considered important to get the prediction. And that's something that will give you, if the task is hate speech detection data, that is something that is giving you a better performance in terms of group fairness. And this is, that's the explained data set. It's a benchmark, and the data set you can find it easily online. And there's something else on interpretability for bias detection. There are some works who have used SHAP to measure bias mitigation. Again, hate speech detection model. There's a strong focus on hate speech detection models. There has been a strong focus on hate speech detection models. In terms of political bias, which a colleague in 2020 did something similar with SHAP. And you can also inspect some components on the transformer. For example, attention scores, which are frequently inspected and studied. And in this case, there's another paper that uses aggregation on attention score to identify which words indicate, again, political bias. So I wanted to give some pointers on this, but I also want to stress the point that there are many different tasks and many different models that we can models and tasks and ways of using interpretability to gain insights and mitigate harmful behaviors. And in terms of gaining insights, if we're talking about misogyny detection, and again, misogyny detection models are binary classification models most of the times. So you have to detect whether a text is misogynous or not. And we have seen similar results. This is a paper from 2022. We have seen that there is a strong lexical overfitting again towards identity terms, first names, and body parts. So for example, if you have a sentence, you are a smart woman, and which is clearly non-misogynous. If you go and look what are the importance scores from some of the interpretability methods, for example, sharp or sampling and occlusion or gradients, you can see that the models focus on the word woman. Of course, you can see that from sharp and sampling and occlusion from this example. And yeah, something similar about, again, lexical overfitting on first names. If you have the same sentence, Anne is in the kitchen and David is in the kitchen, the prediction of the model changes, but I mean, since the prediction of the model changes, goes from a misogynous sample to a non-misogynous sample, you might be wondering, is really the change of the name the first token in the sentence that has changed the prediction, that has driven the prediction? Since it's the only factor that has changed, we can confirm that by looking at the integrated gradients, sharp and sampling and occlusion importance scores. And you can see that the name, the only fact that we changed the name, that's pulling the prediction towards the non-misogynous class. Okay, here I should have said that dark red colors indicate push towards the misogynous class, and dark blue colors indicate pulling away from the misogynous class, so going towards the non-misogynous class. So that's another finding. But what I also wanted to stress is that there was in 2022 a very nice overview survey paper on interpretability methods for fairness in NLP. And after reviewing the recent literature, the authors state pretty clearly that there are a number of papers, although there are a number of papers doing that, only a handful of them apply explainability methods to uncover and investigate biases. So yeah, that's something like a research gap that we might be addressing, especially if there are some younger of you in the audience that want to work on this kind of stuff. There's a lot that we can do, that we can still do. So that's why I moved to the final part of the talk on challenges and new directions. So what are the most difficult challenges with the current state of the NLP? What kind of directions we are going towards? So this is a very strong statement, which I kind of liked, from Sam Bowman in the paper 8 Things to Know About Large Language Models. And Bowman says, as of early 2023, there is no technique that will allow us to play out in any satisfactory way what kinds of knowledge, reasoning, or goals a model is using to produce the output. So this is a very strong statement because we don't have a way, like a formally verifiable way, which is reliable, which is applicable to many models, to understand 100% what's the knowledge, reasoning, and goals a model is using to predict something. So what are the difficult points here? Well, we are shifting paradigms in what kind of models we build and deploy. So one, the size of models. Models are getting larger and larger. And for many of those applications, for many of the existing interpretability methods, it's very hard to scale, like in terms of computational resources that you need. Then there is the point that models are getting, there's this strive in building open models, but there are also companies which publish models under, closed APIs. And the fact that you have closed APIs, that you can just interrogate the model and get the response, doesn't allow you to do many of the to use many of the existing explainability methods. And then there's a whole new different things that are going on today on NLP, novel paradigms, basically for building the models. For example, yeah, the RLHF part. So we have the pre-trained model, then we do this supervised fine-tuning, but then we also, on top of that, add an additional training step based on reinforcement learning, and that's going to change again the probability distribution that the model could produce for specific outputs. So it's not the base model anymore, and you need to take account for that. And also, it's also changing the way we are addressing tasks. So we've been doing classification, for example, since the release of recurrent neural networks with token and word embeddings, by attaching on top of the model, on top of the encoder model, a classification label, a projection that gives you one of the two labels, predicts one of the two or three or more labels. But now we are addressing many tasks just by letting the model produce new text. And that's, again, something that interpretability methods should take into account. And just to give you an example, that's a paper from 2023, market personas. So we know that models have market personas, so they can produce market personas. So when you prompt the model to produce a description of a specific group, a specific social group, social demographic group, actually, you will see, this is a paper from Cheng and colleagues from 2023, you can see that the models are depicting very stereotypical views of specific group members. And this is something that the model is producing, most of the time out of an API. How can we interpret this model? So what are the components of the model? What are the training data set, the training data point? What are it's very hard to frame. It's very hard to tell what really led the model to, in a formally verifiable way, at least, what led the model to produce a specific description of this group member. So there's another problem I have to say, which we should also take into account. Basically, we are assuming that if we have an open model, if the model is mid-sized or in a size that we can use, if there are all the requirements, if all the requirements fit, and we are able to use interpretability tools, we are kind of assuming that interpretability tools are reliable. So the numbers that we get from the interpretability tools, we can use them. So it's not always like that. So let me give you an example. And this is something that we discovered, it's known in the field, but we discovered in a recent paper. Let's say you have the sentence again, you are a smart woman, and you have a compliment detection model. So you are asking, why is this a compliment? The model, you apply your transformer language model. And since it's a binary classification problem, again, the model is predicting. For example, you see that the model is predicting non-complement. And of course, I would not say of course, but given our training data, we know that the true label is complement. So what you can start explaining the sentence by highlighting what are the most relevant words. So you take your explainer, E1, and you get, okay, cool. This is the sentence. Darker colors mean stronger importance. Okay, cool. This is not complement. Since we know there is lexical overfitting, probably the model has lexical overfitted some identity terms. Woman might be one of those identity terms. So we have produced a non-complement because of that. But since you have many methods, many interpretability tools, you can ask a second one. And you have a slightly different highlight in terms of tokens. And so you ask a third one, and you apply a fourth one. And every time you apply these methods, you see that different tokens have been used, have been deemed as important by the explainability methods. Just to say that in the end, most of the times explainability methods can disagree. Explainers, post-hoc explainers can disagree. So you need a way to understand which one is the most reliable and which one you should be using given your use case. So yeah, I'm diving into the final part where I'm introducing two of the works that we have been doing on interpretability, and specifically Ferret is a work that we had at EACL 2023, and it's addressing specifically the issue of evaluating different explanations. So once you have a text and you have several explanations, you might want to have a easy to use way to say, okay, this is the explainer that I should use. So in Ferret, what we focus on is very well-known concepts of faithfulness and plausibility. And in easy, let's say, usability and easy to use APIs. So Ferret at the end of the day is a Python package that you can pip install and test plausibility and faithful metrics. So let me go over very quickly on what we mean by faithfulness and plausibility, and then show you some examples. So you have an explanation, and you might be wondering, okay, but are we sure that those are the tokens that the model really used? How can we be sure about that? So there are some metrics that we can use, for example, comprehensiveness, which measure precisely that. Basically, if you have your explanations and you say, okay, let's take the most relevant tokens extracted by my explanation method, and let's mask them. If I mask them, then the prediction for the specific class should produce a null score. So it should go to 0. If that's really what the model used to make the prediction, if I just mask them, the prediction should go to 0. So that's basically what comprehensiveness is measuring. There are other faithful metrics. I'm not going into the details here, but yeah, it's something that we can discuss about later. And then there is the plausibility. Okay, we matched the explanation with the model internal workings. Now we should also match the explanation with what's our intuition of an explanation, right? So let's say you have intent detection model, and you have sentences where a human is interacting with a voice assistant, and you have a sentence, cancel my 7 a.m. alarm. So you know this is an interaction from a human and a voice assistant, and the prediction is alarm canceled. So a plausible explanation would be this one. So right, so if I'm a human annotating this sentence, I would say, okay, cool. If the target label is alarm cancel, then probably the two most important tokens are cancel and alarm. What you can do, you can check whether the explanation is matching your human plausible rationale. Sorry. So the idea is that you want to have this match in terms of plausibility, and those are plausible for humans. So yeah, that's like a quick slide to show you that it's quite easy to integrate Ferret in your Python-based pipeline. We built Ferret on top of eigenphase transformers. So it's very easy to get the explanations, but it's also very easy to compute several faithfulness and plausibility metrics. So it's everything done from the same class interface, and it's I don't want to say well documented, good enough documented, but on our website. So yeah, since I'm not being interrupted for questions, I think I'll just keep going with the final part and an example on interpretability that helps in building fairer models. So yeah, that's our, let's say, first approach in the direction of let's use interpretability, let's understand what the model is doing wrong, and then change the behavior of the model to build a fairer solution. What we've done is a study on how to mitigate gender bias, occupational gender bias in machine translation through interpretability. And this is a recent paper that we are about to present to NLP 2023. So yeah, let's take this sentence. So we are dealing with machine translations, and I'll get to the point where we discuss about interpretability, but let's focus on the task for now. I have the sentence: the mechanic gave the clerk a present because she won the lottery. Now, in Spanish, you can begin the sentence, the translated sentence, and with el mecánico or la mecánica. So yeah, I'm taking 5 seconds here to let you think what's the correct form here. In this specific example, we can assume, and this is an assumption, this is not like the clear cut, I have to say, but let's assume that whoever wins the lottery is then likely going to give a present because she just won the lottery. So it's a she. So if you look at what are the reference, the she and the pronoun referent to she, the mechanic, you can understand that the translation we are talking about, we should inflect the first two words with a feminine gender inflection, la mecanic. Unfortunately, this is something that the models are not doing. There is a lot of very long evidence of gender bias in occupations, so specific roles are associated with specific genders. So what we did in this work is to, in a way, so first measure this kind of gender bias in the pairs of languages, English, Spanish, and English, German. And we focused on the YMT dataset, which is a standard benchmark for occupational stereotypes in MT. But what we wanted to bring to the table for the first time was the study on instruction fine-tuned models. So these kind of models that you can use, that you can apply for many NLP tasks just by prompting them. And then we use interpretability to run the biasing, to apply the biasing to these models. Quick intro on instruction fine-tuning. The idea that any NLP task can be described with an instruction gives you a way to fine-tune a sequence-to-sequence model to produce the output. So given some prompt, the model, if prompted accordingly, the model can give you the prediction. So with the same architecture, here I'm showing T0, which is a transformer sequence-to-sequence model. With the same architecture, you can solve many tasks just by prompting the model differently. You can run summarization, sentiment analysis, question answering, and so on. And what we know is that we can also have zero shot. So the model is also learning some zero shot capabilities on unseen tasks. So yeah, this is a very short overview of the whole paper. So sorry if it's like super condensed, but let's go from top to the bottom, and then we're done basically with the idea. So you have the sentence, the mechanic gave the clerk a present because she won the lottery. So we know that the she is the anchor that the model should use, is the gender clue. So actually is the lexical clue that the model should use to decide whether we should start with el mecánico or la mecánica. So what we can do is compute the attribution scores, so compute interpretability scores that tells us how strongly the model has observed the pronoun. So ideally, you want the model to look very in a very focused way to the pronoun to decide the translation, how to begin the translation. So what we discovered in the paper is that models frequently overlook the pronoun. And this is interesting because this is kind of expected, I have to say. But what you could do is, okay, you have for each sample, how badly, let me use the term, how badly the model overlooked the pronoun. And then you can say, okay, those are the examples where the model completely overlooked the pronoun. So it just used its biased representation of the profession. And so those are the examples that you should provide to the model as few short examples to produce a better translation, a fairer translation. So you use interpretability, you compute interpretability scores, you pick what are the most relevant examples for the task, the ones that have where the model has overlooked the pronoun the most. Then you let human translators translate them, and you use them as few short prompting. So like an expanded example of this would be, you have a model, which might be T0, T5, any model, and you ask the model, translate the following sentence into Spanish. Again, the sentence you already know what that is. And error, you have a misgendered translation because you should begin the translation with la mecánica. Then you use interpretability, and this is basically an extended version of what I've shown you in the previous slide. For every example in the V90 dataset, you go and look, okay, so let's use interpretability to see what are the examples where the model completely overlooked the pronoun. So what are the most relevant cases? And for example, what we found is the mechanic hired the assistant and gave him an orientation, or the second one is the manager asked the accountant for the books because she felt the work was wrong. So let's imagine that those are the examples where the model completely overlooked the lexical clue about the pronoun given by the pronoun. And then we go to human translators and ask for reference good few short translations. And so you get the translation, for example, this is for the first sentence, el mecánico contrató al asistente y le orientó. And then those become your few short examples. You prepend them to the prompt, and then you ask again, please translate the following sentence into Spanish. And with this prompt, basically it's few short prompting, you get the correct translation. If you do that across the two languages, two sets of models, two families of models, for the cases where we basically we have in binary T, you get increased accuracy, but also more like fairer translation, because what you are having is basically the same accuracy across the two genders. So of course we should not consider gender as a binary variable. In the paper we also explore gender neutral translations where you have in English form you have the neutral pronouns, so they, them, or their, but we have different insights there because the models frequently don't use any gender neutral translation or any gender neutral form or a phrasing in the translation. So we are quite far for, gender neutral translation. But for the binary case, by doing few shot, you can get a fairer model because you almost, you balance the disparity in terms of accuracy, because you produce, especially in terms of misgendering female actors, you kind of balance the performance of the model across the two groups. So yeah, that was like a condensed version of the paper. Feel free to, ask more about that. Feel free to, I don't know, reach out if you want to discuss or, I don't know, criticize our ideas. Yeah, with that, I'm basically done with the talk. I hope you liked it, but I'm super happy to get questions and ideas anyway.
Yeah, thank you very much for the talk. The last paper is very interesting. I was thinking, what happened if you use chain of thought to improve the translation. Do you perform some experiment using chain of thought instead of few shot?
Okay, so in the paper we don't do that, because in the paper, so there are many answers. So it's a very, very topical question, very important question. So thank you that you made that. Basically, in the paper we don't do that because we use instruction fine-tuned models. So like FLANT-5 or MT0, which are models that are not known for, they are too small and they're not known for having chain of thoughts capabilities, because they are not conversational agents, they're not large scale based models. So you cannot use chain of thoughts because they have been fine-tuned on instruct proper NLP tasks made verbalized into instructions. But we are exploring the chain of thoughts approach with larger models, like state-of-the-art Llama, for example, models, especially because there is, wait the example here. And this is something that we are quite interested into exploring, because look at the sentence. The mechanic gave the clerk a present because she won the lottery. So we can assume, so the model here is doing, we are asking the model to do, to me, I have to say 3 tasks. So you have to leverage some sort of common sense word knowledge, because one, you need to understand that, if sorry, it's happening something on my camera. You have to understand one, this is crazy. It has been happening to me like multiple times. Sorry. Okay, one, you need to understand, you have to have some common sense knowledge that if you win the lottery, you might be willing to give a present to someone. Second, that understanding, the common sense understanding, should help you in doing the co-reference resolution. So you should know that she, given that common sense knowledge, is referring to the mechanic, because the sentence itself can also be read as she referring to the clerk. I mean, the clerk won the lottery, but the mechanic gave her anyway a sentence. So it's not grammatically and semantically and syntactically incorrect, right? That she can refer to the clerk instead of the mechanic in this specific sentence. And 3, the model has also, to perform to pick the right tokens and do the translation based on that information. So yeah, just to conclude this very long answer, we are testing chain of thoughts by asking the model to identify the authors. So who do you think won the lottery? In this specific example, can you explain? So can you explain who do you think has won the lottery? Who's giving the present to whom? And then given that information and that logical steps and logical reasoning on those two steps, please translate the sentence. And it's very, very, I don't think there's something out there doing this kind of stuff. So I don't think we will have, I don't know, good research. I don't know, actually, no, I think it's interesting to see what's happening with largest models. Yeah.
Yeah, well, with this example, I was thinking self-ask. I don't know if you saw it. This kind
Which
of
one?
prompting, self-ask. It's a kind of.
Oh yeah, the self-ask.
When you just
yeah.
compose a task in simple task using follow questions and then conclude as.
Yeah, it's kind of very similar to that. Our idea is very, very similar to that. We're kind of prompting the model in different ways, but it's very similar to that.
And another question with this paper,
Sure.
do you test if what happens if you add some kind of tokens in the prompt? For example, translate fairly the following sentence.
Okay,
or something like that.
Okay, that's another the biasing approach from. I don't remember now the paper. It's an Anthropic paper, but this one we tested that, and again for Flan and MT0 models, you cannot steer the behavior by including some additional tokens.
Okay.
And I'm expecting that's because again the training data, the fine-tuning data that it has been used. But there is a paper on I think again from Anthropic where the researchers have shown that if you prepend produce an outcome in an unfair way and non-discriminatory way to this task, and then you append the task, for example, translate the following sentence, you get overall a fairer output, I would say. I don't remember now which task they were addressing, but which set of tasks. But I can share it with you, the paper. I don't remember now off the top of my head. But we tried that with 25 and T0 and it didn't work. When we were basically we started from using computing interpretability scores and seeing whether the model overlooks the pronoun or not. Then we discovered that the model overlooks the pronoun. And then we were like, okay, cool. How do we fix that? And then we started testing different approaches. We tested parameter efficient fine-tuning. We tested prompting with the self-debiasing prompt. I don't remember now the name, this Anthropic paper. We tested few-shot learning, and what was happening is that, few-shot learning was the only solution that for those models was kind of working.
Nice.
Which is this one.
Any question? I have another question. I don't know if anyone have other question.
I have my question too. So you mentioned the unreliability of interpretability models or queries, and this has been mentioned before in a talk, and it really ranked back to that because I wonder two things. One is whether you believe there are risks for having a misinterpretation for a certain model in terms of bias, whether for example, as if misinterpreting the model with unsuitable interpretability method will say that the model is unbiased when it isn't, and we end up fair watching the model. And so it goes on this side, whether you've evaluated risks for misinterpretation, and if you believe that FAIR can eliminate or mitigate these risks.
Okay, that's a super interesting question. That's super on point, I have to say. So first, yes, I think there are like I had a slide in this talk and then I removed that. Who's watching the watchers? Basically, we use interpretability methods because we kind of need something that tells us, okay, this is something expected, this is something not expected, or act on the model. But then who's watching the watchers? So can we reliably, assess that those are reliable, valid explanations? And we can take decisions, like serious decisions on, it's not only like, for example, considering a model by unbiased when it's biased. We can, for example, say, look, this is overall, the model is using overall what my humans would use to produce the output. So I'm expecting it is kind of acceptable, and I'm going to deploy it. But then, that might be wrong. For example, the explanation might be not faithful. So whenever you're looking at an explanation, if the explanation is not faithful, the model is using completely different. Now, this is what I've done, what I presented today is like short examples. But let's imagine you have like a long text, like a long tweet. If the explanation is not faithful, whenever you look at the explanation, you are looking at the wrong thing. And you might be, I don't know if in terms of bias, what that, of course, yeah, that's also related to what you were saying. If you consider a model, if your model passes the bias bar, the bias checks, it gets deployed. And then you might have some discrimination when the model is deployed, and you don't want that. So yeah, I think Ferret goes in the direction of, I would say, streamlining the evaluation of interpretability. So now it's a Python library, so it's not like much more than that. But since it's built on top of a library that everybody's using, I would say now it's kind of too simple to evaluate your explanation that you should do that. And if you don't do that, then you might be, overlooking something which is like meaningful. Let's say you have an application where you provide some humans the explanations and you don't, do the effort of evaluating them. Today with Ferret, I think it's quite easy to do. The library has still some bugs laying around, but I think it's too easy to not to do that. And I think goes in that direction, yes. So making it too easy to avoid the interpretability, the evaluation of interpretability. And yeah, I would say, yeah, in that direction, yes, definitely.
Great, thank you.
You're welcome. You're welcome. I just want to add something here. Ferret it's not that much, it's not super downloaded, but we still have like $500, $600 downloads per month. So we believe that someone like is starting to use it it's a research product, of course, but we see some traffic and some people installing it. So I think we are in the right direction, and we are currently working on extending the interface, including more easy ways of solving different tasks. For example, NLI, I don't know, named entity recognition, zero-shot classification, question answering, this kind of NLP tasks where you use an encoder model to solve it.